Hey there, chemistry students. This is Ms. Ruark. It's podcast 4.4. We're going to talk about how moles can help us determine the volume of a gas, and how the volume of a gas can help us determine how many moles we have. All right, so volume is something that varies with a change in temperature or in pressure. So the volume of a gas is usually going to be measured at standard temperature and pressure, or what we call STP, standard temperature and pressure. And the conditions for standard temperature and pressure would be 0 degrees Celsius, which is the temperature at which water starts to freeze. And the standard temperature would be 101.325 kilopascals, or 1 atmosphere. Now, typically this is the one we'll come up with, is 1 atmosphere. Right, and we will talk about the gas laws, and we'll talk more about how this volume changes with change in temperature and pressure, but we're not going to worry about it right now. Okay, so volume at STP. At STP, or standard temperature and pressure, 1 mole of any gas fills 22.4 liters. This would be what we call the molar volume, because it's the volume of 1 mole of a gas. Okay, well, at 22.4 liters of gas at STP, or standard temperature and pressure, well, how many particles are there? Well, let's think about it. If 22.4 liters of anything, of any gas, at standard temperature and pressure is equal to 1 mole, and we know that 1 mole is equal to 6.022 times 10 to the 23rd particles, then 22.4 liters of any gas at standard temperature and pressure has to have 6.022 times 10 to the 23rd particles. No, it's just another conversion factor. It's another way for us to account for the number of particles, number of atoms or molecules that are reacting in a gas this time instead of in a substance. All right, so molar density. Well, density is equal to mass divided by volume. Okay, so the molar density would be equal to the molar mass of a substance divided by the molar volume of that substance or that gas. All right, so the molar density, which would be the density of 1 mole of any substance, would be equal to the molar mass divided by the molar volume. Okay, well, molar volume is always going to be 22.4 liters. So when we're trying to figure out the molar density of a gas at standard temperature and pressure, the only thing that changes here is the molar mass of that gas. Okay, and it depends on the substance. If you have oxygen, it'll be 32.0. If you have hydrogen, it will be 2.02. It depends. So this part changes, whereas this one stays the same. And to find the molar density, you would take the mass divided by the volume. It's pretty easy, right? This will come more into play when we get into the gas laws. I just want to introduce it for now. All right, so how do we use this 22.4? Okay, so here's some problems that we'll go through, and it says how many grams, so this is what we're looking for, how many grams, so we're looking for mass, are there in 1.5 times 10 to the 25th molecules of CO2. So here we have particles. Okay, we're looking for mass. We've got this many particles, and CO2, guess what? This is a gas. Woohoo! And if it doesn't state it, we're going to automatically assume that it's at standard temperature and pressure. If it's not at standard temperature and pressure, it will most likely tell you in some way, shape, or form what the temperature and what the pressure is. And if that's the case, we're dealing with gas laws, and that's not what we're doing right here. So for right now, we're going to assume that everything is at standard temperature and pressure. All right, so if I have 1.5 times 10 to the 25th molecules of a gas, okay, to get from the gas to grams, from molecules to grams, well, you guys know how to do this, right? All we have to do is go from molecules to particles to moles, right? Whenever in doubt, go to moles. And then from moles, can I go to mass? Well, yeah, I sure can. I can just use my molar mass to get from moles to mass. So there's nothing new going on here. This is the same thing that you've been doing this whole time, right? From grams to moles, or from particles to moles, or moles to particles. All right, so set up the problem. On the bottom of the next fraction, we put molecules of CO2. And we want to go from molecules to moles, so we've got to put mole on top. And remember, molecules and moles, two different things, not the same thing. Don't use them interchangeably. All right, we know that 1 mole of any substance is equal to 6.022 times 10 to the 23rd molecules of that substance. And so now our units will cancel. But we're not done yet. We want mass. So let's keep going. All right, on the bottom of this next fraction, we're going to take moles of CO2 and pull it straight down so that they will cancel out. All right, well, we want to find grams or mass of CO2. So the number that goes here in the top is going to be your formula mass. So we have to take CO2 and we break it down. There's 1 carbon, 2 oxygens. The mass of carbon is 12.01 and the mass of oxygen is 16. So 12.01 plus 32. I know, it's becoming a hot mess over there. I need to erase some of that. Let's get rid of it. There we go. Okay. So this plus that equals 44.01 grams per mole. All right, so we know that 1 mole of carbon dioxide would be equal to 44.01 grams of carbon dioxide. Moles cancel. We're left with grams in our unit. That's what we're looking for. So now we can just solve the problem. So let me grab my calculator. And we know that we have 1.5 times 10 to the 25th times 1 divided by 6.022 times 10 to the 23rd. And then we need to multiply that by 44.01 and divide by 1, right? All right, so how many grams do we have? This is a lot of grams. 1096.230 blah, 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 blah. Let's look at our significant figures. We need 2 significant figures. So the 1 counts, the 0 counts, everything else behind it is simply a placeholder. So this becomes 1100 grams of carbon dioxide. Now, if you don't like that, you can also change this into scientific notation, and you could say it's 1.1 times 10 to the 3rd grams of carbon dioxide. Either one of these 2 answers would be correct. All right, so what volume would the same carbon dioxide occupy at standard temperature and pressure? Now, you can start here at molecules of carbon dioxide, or you can start here at grams. I'm just going to use the number they gave us in the previous problem. And I'm going to say 1.5 times 10 to the 25th molecules of CO2. And we're looking, remember, we're looking for volume, right? We're looking for volume, so we're going to liters. And we've got to get rid of molecules. Remember, whenever in doubt, go to moles. So we want moles of CO2. And we're going to put molecules on the bottom. All right, well, 1 mole of anything is equal to 6.022 times 10 to the 23rd. Molecules cancel. We're left with moles, but we don't want moles. We want liters. So we're going to put moles on the bottom of the next fraction. We're going to put liters on the top. And we know that 1 mole of any gas at STP is equal to 22.4 liters of that same gas. Moles cancel. We're left with liters, and that's what we want. So now we take the calculator and we do the math again. So 1.5 times 10 to the 25th times 1 divided by 6.022 times 10 to the 23rd. And then we multiply that by 22.4 liters divided by 1. And the calculator gives us 557.954 ... Go back. We want 2 significant figures again. All right, so we're going to have 560 liters of carbon dioxide, or you could say 5.6 times 10 to the 2 liters of carbon dioxide. Remember, these are the same numbers, so it doesn't matter which one you give me. Okay. All right, so what is the molar density of carbon dioxide at STP? So remember, to find density, we need to have mass divided by volume. And since we're looking for molar density, we need molar mass divided by molar volume. All right, so molar mass would be 44.01 grams per mole. Grams per mole. All right, and the molar volume is going to be equal to 22.4 liters per mole. And so we take the 44.01 divided by the 22.4, and we end up with 1.96473 ... We need 3 significant figures, so 1.96 grams per liter. That's all you got to do. Okay? All right, so I think that's it, guys. Oh, and this right here is in your notes. This just shows you a simple roadmap that you can follow that shows you how to get from moles to volume, from moles to mass, moles to particles, and vice versa. So use this whenever you're in doubt. This is what we call a road map. I know you guys don't need to use those anymore because you have GPS, right? But this would be like the GPS. It just doesn't tell you. You have to read it to figure out where to go. All right. And, all right, I'll see you in class.